So last time we talked about the ascending pathways, and the time before that was the receptors. So you have receptors, somatosensory receptors with all these different kinds of information. And then we've got the ascending pathways, the dorsal column pathway that comes up to the ventrobasal nucleus, that goes up to the cortex. And then we've got the spinothalamic pathway that goes up to the, it comes into the spinal cord, and then it projects up to the posterior nucleus and the intralaminar nuclei, and then and now we're going to talk about, let's go up to the cortex. So what are the cortical areas, like we talked about the cortical visual areas for the somatosensory system, and what is the organization of these maps look like? And in particular, there's kind of a big difference between the visual and the somatosensory maps, and so we'll go over that difference. And we'll go over what's the reason for that difference. And then we'll talk about plasticity, because it was discovered a while back that some of these maps are actually movable. And at the end, we'll sort of come to the surprising conclusion about where this movability is actually occurring. It's actually not occurring in the cortex, even though we're measuring it there. So let's start off with, where is the somatosensory cortex? If this is the central sulcus, then the somatosensory cortex is basically behind the central sulcus, but it also goes into the lateral sulcus, like that, and it also goes around the edge. So there's some somatosensory cortex that's kind of on the midline, especially like the feet, some part of the feet, and there's also some somatosensory cortex that's actually inside the lateral sulcus. And so that's the somatosensory cortex. Doesn't look very big, and we said last time that in a primate, visual cortex is much bigger than somatosensory cortex. Visual cortex is about half of the cortex, and somatosensory cortex is only like about 1/8 of the cortex. So it's about 1/4 as much cortical territory as the visual system, because we're such visual animals. And if we cut a section down through there, what does it look like? Well, you've got, you have the cortex going over the top here, and then it comes down to the lateral sulcus, and the lateral sulcus sort of goes in like a little mushroom shape. And so, if here's that cortex coming like that, you have this sort of mushroom shape there called the insula. So this thing is called the insula. And the insula, it's a place, but there's a whole bunch of stuff in there. So don't get the idea that there's something like deep and dark about the insula. It's got some somatosensory cortex, it's got some auditory cortex in there, it's got some motor cortex in there, it's got some, vestibular cortex involved with sort of figuring out what direction your head is tilted or rotating. So this guy is the lateral sulcus, or the Sylvian sulcus, lateral sulc. And if you go down further, there's another big sulcus right here, which is the infratemporal, the superior infratemporal, the superior temporal sulcus, and then it sort of comes around hippocampus over here. So this guy is the STS, the superior temporal sulcus. So where are the somatosensory areas? Well, they start up, over the midline. So this, here's the midline right here. So they start actually just over the midline. In a human, less over the midline than in a monkey, and they come down, and they actually go into the insula there. So if we unfold that whole thing, like I like to do, what do you get? So we get area 3B, and so it's a long extended thing like that. So that's area, that's called area 3B. So where do those numbers come from? So those numbers go back to Brodmann from 1909, early 19th century, when they looked at the cortex and they found, well, the cells look a little different. And there's another area behind it called area 1. That looks like another little thin strip. And there's an area in front of it called area 3A. That wasn't even a distinction that Brodmann made. So afterwards they subdivided it into area 3A and 3B. And sometimes you wonder about the numbering system, 1, 3, and then what comes after 1? Well, 2. So did they have to do that? So here's 2. There's area 2. And then behind that there's a number of additional areas. Generally there's area 5 behind it. But it turns out if you actually look at this region here, you pretty much have a map of the body surface pasted on top of a map of the visual world. And so there's like, the leg is down here, and the torso, and then the face, a big face representation there. No arm. So the arms are kind of movable, like, so what's present in this area? So what is that area? This area is VIP. And we'll talk about it more later on, ventral intraparietal area. So that has no hand in it. And if you go a little bit further over, you've got hand over here with some visual stuff on top of it, and a little bit of leg also, especially the movable part of your leg. And that area is called AIP for anterior intraparietal. So this guy is VIP, and it's kind of divided up. And here's AIP. So AIP is like a somatosensory plus visual area, but for the time being, we'll sort of like call it somatosensory. And then as you go down into the lateral sulcus, you have a series of areas down in there. It was originally called S2. So what is S1? Well, initially what happened was people looked at the representation of different parts of the body in area 3B and 1 and 2, and it turns out if you look at this, you can see there's generally sort of the foot up here. And what do we mean by the foot? We mean like, the leg and like maybe the buttocks and a couple, more than just the foot. So the lower leg, the upper leg, the foot, the toes, everything. And those representations of the foot are lined up more or less across 3A, 3B, 1, and 2. And then when you go further out here, you see that you've got all these guys have, face, including scalp and eyebrows and part of the neck. And then here's the hand over here. And the hand includes like, the hand and the arm and the shoulder. So we'll just call it foot, hand, face. So when people first looked at this, they said, well, it looks to me like we've got a foot, hand, and face. And so they called this whole thing S1. Ooh, but did I have to draw it right on top of the hand? So the original so Brodmann in 1900 already had subdivided it, but then later on people said, no, just this whole thing is S1. So that's where S1 comes from, and then S2 was supposed to be the second higher level somatosensory area. But it turns out when in the 1980s, people went in great detail and discovered actually there's 4 representations of the body surface in area 3A, 3B, 1, and 2. And the way they found that, how do they miss it? Well, they're just very close to each other, and so if something is repeating, like you have another copy of the hand, unless you're going really carefully, you won't actually find that there's actually another copy there. So when they did that in S2, they discovered there's another area in front of S2 that's a copy of another copy of the body, and there's a couple additional areas in front and back, and then there's an area generally out here that has various names, but sometimes people call it 7B. It also has some multisensory input, and so that pretty much got another area, the retroinsular area there. So that pretty much covers these visual maps. That's sort of a reasonable summary. So not as many as we have visual maps, somatosensory maps. So not as many as we have in the visual system. The visual system has like 30 or 40 maps. Here we've got 1, 2, 3, 4, 5, 8, 9, say 10, 12, something like that. But these are multiple copies of the body surface. And so how are these discovered? So let's zoom in on the hand representation. And so where is the hand representation? Let's just zoom in on the 3B hand representation, which is located about here. So that's the actual fingers. So just put fingers. So if we zoom in on that, what does it look like? Well, it's kind of a little complicated. So let's draw it down here. So I'm just showing area 3B and 1. So here's area 3B and 1, zoomed way in. There's only a couple millimeters across this. And so if we look at area 3B, so here's area 3B and area 1. So what we can see is you can actually see the individual fingers, and the individual fingers are these little strips like this. So you can actually see. It turns out you can actually see them in the cortex. So there's little strips like that. So so this is 1, which is the thumb, and then 2, 3, 4, and then 5 is a little finger. So you see them out like that, but which way is it? This is the palm here. So these are the fingertips. So the fingertips are here. The fingertips are facing forward. So this is the fingertips. But if you actually look at what is being represented, so if I draw a little monkey finger here, or a human finger like this, and that sort of goes down, and here's the top of it, and there's the fingernail, and there's okay, so that's not a very good drawing of a finger. So if you look at your finger, you can see that the top of your finger has a little hair on it. So the top of your finger, it won't have a lot, depends on how hairy you are. But if you just look at the top of your finger, you see hair follicles especially on the base joint, you'll see hair follicles on top of your finger. And if you look underneath your finger, no hair. And so those two parts of the finger, so this is called hairy skin. That's actually the name, the technical name, hairy skin. And you have a lot of hairy skin. And then this part's called glabrous skin, which means hairless skin. And like I said, if you look at something like a spider monkey, the spider monkey has some hairless skin on its tail. It's got a fingerprint. And this glabrous surface, will have a little fingerprint. And so what is that fingerprint? Well, each little ridge of that fingerprint has like a little Merkle disc in it, It's got its own little Merkle disc in every ridge of your fingerprint. And so it's really good at detecting little shape of things. Hairy skin, not so good because there's hair sticking out, and so you can't sort of distinguish the shape and the texture of objects. So the glabrous skin is really good for touching stuff, figuring out what it really is. So it turns out this representation here is just the glabrous skin. And so where is the hairy skin? Well, it's shoved off to the side. So there's little patches over here that are the tops of the fingers. So the tops of the fingers are sitting sort of off to the side of the, it's too many fingers. I need 5. So it's kind of strange. So what you did, so how does the somatosensory system work? It's actually not like the visual system at all. It's a bunch of little patches. It's a bunch of little patches of skin, so the underside of the skin, the underside of the fingers are sitting there, but then the sitting here, but the tops of the fingers are sitting off to the side. And if we go into area 1, you see something that's even stranger. And so as we go into area 1, we find another copy of the palm. And how do we determine that? Well, if we just record, say we record across the middle finger representation, you find it's responding to the middle finger, and then eventually you get to the palm. As you continue backwards in area 3B, you run down to the palm. And then what happens when you go into area 1, you go back over the palm again. So you've got another copy of the palm. But then when you look at what happens in the finger representation, there's a little bit of the underside of the finger. And then there's the top hairy surface of the finger stuck right in there. The entire top hairy surface of the finger. And then as you go out to the fingertip, you got like the representation of the fingertips again. And the same thing occurs in the foot. So if you look at the representation of the foot, you see the same thing. We have no idea what this is for. It's very clearly present in all primates. Somehow area 1 has taken so this is hairy here, and this is glabrous, meaning no hair. And so the hairy part is just pasted in between the bottom part of the finger and the top part of the finger. This is hairy. So this is fingertips here, fingertips at this end here. So yeah, kind of a strange world down there in somatosensory cortex. But what is the difference? So I mentioned that there's these little patches, but what does that mean? So what does that mean? So that's our basic somatosensory cortex, but how does it differ from the maps that we have in the visual system? So, because we talked about discontinuities in the visual system, like you have V2 has a representation of the upper field that's separated off from the lower field. So, you've got that issue, but this is something different. So, if we start off in our visual system, one thing that we find is if we now think of something, so when we talked about discontinuities in the visual system, we talked about we're moving something across the horizontal meridian and suddenly it jumps to some other part of the cortex. That was a discontinuity. But let's look at it the other way around. So the other way around is move small distance in cortex. So move small distance in the cortex, and what you see in the visual system is that virtually always, there's a few exceptions of course, virtually always small movement of the receptive field. And so what does that mean? It means if we go into the cortex, so here's a little chunk of cortex. That's our cortex. And if we record, so we put an electrode over here, and then we move it a small distance. What is a small distance? Like, less than a millimeter. Just a small distance. And then look out in the visual world. So look out in the visual world. So say that was the, left hemisphere. So now we look out in the right visual world. So here's the right visual world. So we look out there, and what happens is, say we were in the lower visual field, we'll find one receptive field like this, and then we move a small distance and we get another receptive field like that. That's just close by. And that's always true, virtually always true in the visual system. And so what's one sort of rationale for this? Well, if you think about how the visual system works, it's got a retina, and the retina can sweep over the world. It can look at different things and sweep over the world. But, the world's complicated. It's got there's a big tree back here, and there's, some, house here, and there's, stuff in the foreground. Somebody's walking around, all this stuff. And we've got a retina, we're just sort of sweeping over this whole thing. And every once in a while, we'll look at, say we fixate right there, in which case, this part of the retina is seeing something very different from this part of the retina. But on average, what happens is, if you're in the retina somewhere, your neighbors are almost always going to be stimulated in a similar way, on average. So it's rare that you always look exactly at one edge so that a particular part of your retina is stimulated one way and another part right next to it is stimulated a different way. That just doesn't happen. You just look at all this stuff. And so in general, what's going to happen is nearby points in the retina are going to be stimulated similarly. And if you imagine you have some kind of Hebbian learning, that would strongly drive, maps that don't have discontinuities in it. And in general, visual maps don't have this kind of discontinuity in them. But if we look at the somatosensory system, I'm going to leave space for a 2 here. Okay, so if we look at the somatosensory system, it's different. And so how is it different? Well, when we move small distance in the cortex, we often get a jump. A jump in receptive field. It might go to some other part of the body. The simplest case would be right here. If we make if we're recording from the middle finger, say we record from the middle finger, and then we get another receptive field on the middle finger, and another receptive field, then we come up to the edge of the middle finger. When we go across that little boundary onto the index finger, what will happen is the receptive field will never be partly on the middle finger and then partly on the index finger. It'll just jump over to the index finger. But that's a small jump. It's just like from one finger. But it turns out, if you look at the somatosensory system in detail, there's thousands of these jumps. So an example is the chin is right here, right next to the thumb. This is the chin. So what that means is if you go off the edge of the thumb, off of the hairy surface of the thumb, so you go from like, you're recording right here in the hairy surface of the thumb, and you go just a tiny bit further in area 3B, and then suddenly the receptive field just pops onto the chin. And then, as you continue on, it'll sort of like move along the chin. So there's these hundreds of these discontinuities across the cortex. And why is that? Well, if you just take the fingers, I can easily just touch one finger, just touch my index finger, and without touching the other fingers. So that's one possible reason. It's much easier to stimulate, just systematically stimulate just my index finger and not touch that's something that's very hard to do in the visual system with a part of the retina. You just repeatedly stimulate one part of the retina different than a nearby part of the retina. Very easy in the somatosensory system. But the other reason is, for these discontinuities, is think about what you're trying to do. You're trying to take your body surface. Now look at your body surface. Imagine it like a rubber sheet. Now strip off your body surface, and now you've got to paste it on a two-dimensional cortex. How can you do that? Obviously, if you tried to kind of like just stretch it and take your, like your bodysuit and stretch it onto the cortex, there'd be a huge amount of distortion. And so what does the somatosensory cortex look like? It doesn't look like the visual system where you take the retina and you just map it onto the cortex. That you can do that without, especially if you cut the retina in half, you can quite easily map a quarter of a sphere onto the surface without stretching it very much. Somatosensory system, what you do is you just like snip, and paste all these little patches into a little quilt. That's what somatosensory cortex looks like. And this concept, if you ever look in a textbook, you'll see like a homunculus, like a little person mounted in your somatosensory cortex with big lips and big hands and big feet. That's because people can't quite get the idea around that it's actually not like that. What it is you just like snip on the bottom of the fingers, and you pasted this whole quilt together with hundreds of little pieces. So the maps in the somatosensory system are quite different. They got all these little discontinuities in them. It's very different than the visual system. Now, this, just to sort of put it in perspective of what we talked about before, there's another way of looking. We could move small distance in visual field. And sometimes a jump. So that occurs. And one example was if we cross the horizontal meridian. So if we cross the horizontal meridian, what would happen is, there's the horizontal meridian. As we go across the horizontal meridian, as soon as we cross the horizontal meridian, we suddenly jump. So we're going 1, 2, 3. And there's a jump on the cortex. So if we were in V2, in the lower field, we would be on the upper part of V2. And then when we cross the horizontal meridian in the visual field, suddenly it jumps to the upper field V2, which is sort of downstairs, it's lower. So that kind of discontinuity, that also happens here. That can happen here too. Also here. But how can these two coexist? So let's just take an example. So if you look at V1 in the cortex, it looks like this. There's the lower field and the upper field. That's V1. V1. And then we know that V2 is got this split in it right here like that. It's sort of split so that the lower field part of V2 is in a different place than the upper field part of V2. So here's the upper field part of V2. So that's the lower field, and this guy is the upper field. There's the upper field. So there's no break in V1, but you can see you've kind of pried the lower and upper field apart. And so this is the discontinuity here. Let's draw that one in. So that's a discontinuity. But what happens at that discontinuity if we try this first test? So if we try that first test, so then we have to talk about what's next. And so what's next is there's another area called V3. So here's V3, the lower field part of V3. And what happens if we go across that boundary? So I would be in the lower field of V2. I would come up to the horizontal meridian, and then I continue moving a small distance in the cortex, and I go into the next area. And what happens? I just go back into the lower field. And so it's still a small receptive field move. So even at a place where there's a discontinuity, when we think of it in this, starting in the visual field, do we jump when we go on the cortex? Even in a place like that, which is the front border of V2, it's still the case that when we make a small distance move in the cortex, it always makes a small distance move in the visual field. So it's possible to have this kind of discontinuity without having that discontinuity at a point. But the real point is, what is the cause? What is the cause of this? And the cause of this is different correlation structure of vis versus somatostim. It's very easy to just touch the chin and not the thumb. It's much harder to do the equivalent thing in the visual system. Okay, so that was talking about these differences. So there's maps, but they're very different. The somatosensory maps are cut up into hundreds of pieces and all pasted down on the cortex, and there's all these little discontinuities, and that's not the case in the visual system. The visual system has these continuous representations. Okay, so any questions about the whole somatosensory system? Area 3B. Any question? Oh, that must have been next door. It's a little confusing about all the discontinuities, but just think of it from a practical point of view. How are you going to represent the complicated body surface, like the hand? Look at the hand. Look at the surface of the hand. How are you going to get that onto a two-dimensional sheet? Because the cortex is just a two-dimensional sheet. So how are you going to represent that complicated shaped surface on a two-dimensional sheet? You got to cut. So any other questions? All good? I've erased all the things that you might ask questions about. Okay, so for the last bit, let's talk about plasticity. So when these maps were first discovered, the fine details of these maps were first discovered, if you want to, I put one of the readings in there. There's So there was this well-known paper with Merzenich and Koss in 1978, and that's when they finally really mapped these things in very fine detail. It's very good to go back to that paper because it's kind of easier to read in a way than more recent papers, but that's where they figured out there were these, there's maps all over the place, complicated maps with little patches. That's where they figured out, that's where they originally figured out that business about area 1 intercalating the hairy part in between the top and the bottom of the finger for God knows what reason. So what they did soon after that was to see, are these maps fixed? And these experiments were almost all based on, so Merzenich was up in San Francisco in contact with some of the hand surgeons up there. And so these experiments were all based on basically things that human hand surgeons had developed for the purpose of fixing you up after you got in a car accident. So if you get in a car accident and get slammed, it's gonna mess. You got about a 1% chance of that happening in your lifetime. It's going to seriously mess things up. 1% chance of dying, actually, in your lifetime. So, so the very first thing they did was, let's just cut a sensory nerve. So if you cut a small sensory nerve, like the radial nerve, what the radial nerve services is it services your thumb, index, and middle finger, but half of your palm and the little finger and the fourth finger and the wrist and everything will still be working, but your thumb, index, and middle finger will become numb. And this commonly happens in a car accident. And so if we go into the cortex, and so the first thing we could do is denervation. So let's cut the radial nerve. And so we go into the cortex and first map the cortex, and you'll find there's the thumb. So the thumb, and then the other fingers all lined up. Now cut the radial nerve, and then go in. So cut radial nerve. So there's quite a difference between cutting and just crushing. So I have had some experience with a nerve crush. Once I was doing an experiment, and I sat cross-legged for about 90 hours or something like that, with a few naps in between. And when I finally got up, I said, "Well, I can't really feel my toes." So it turns out if you've got a nerve, the way nerves work is they have these little cable covers. They're called perineurium. And then inside the cable cover, there's a single axon. So there's a single axon inside the cable cover. So if you just crush a nerve, like squeeze it really hard, you won't actually damage the little cable tubes. So the cable tubes will still be there. So what will happen is, so like if you crush it, what will happen is it will kill the axon, but the little tube is still there. And so the tube is still there, and so what that means is that all that has to happen is the axon is connected up to a dorsal root ganglion cell. The dorsal root ganglion cell didn't die, and so then what will happen is the part that's on the other side of the crush will die, but then it will just slowly grow down the tube, and when it gets to the skin, it tells the skin, I need a Merkel disc, and so make another Merkel disc, and then the skin makes a Merkel disc, and then it attaches up to it. And so all I had to do was wait a month or so, and slowly but surely I could sort of feel like, now I can feel the bottom of my little toe. Now I can feel the top of my little toe, and everything just grows back. So crush is good. If you just crush, it will just come back. If you completely cut it, now that's not so good. And so sometimes what they do when they're doing hand surgery is they just say, "Oh, you cut your radial nerve." And so what they do is they find it, and they just sew it together. And what happens is it's like a patch at the phone company. They're not hooking up the right wire, and so the right wire will just grow into any old cable tube that's there, And so you get kind of a jumbled representation. Not as good, better to not cut. But anyway, if we go back to just cutting the radial nerve, and not attaching it to anything, what happens? Well, in a short period of time, we're talking about like just 2 weeks. What happens is 4 and 5 take up almost all the space. And so almost all the space that was cleared by damaging the nerves that are going to the thumb and the middle finger will be completely occupied. So somehow these guys moved. They kind of moved. And so once that first experiment was done, people said, wow, these representations are all plastic. They're all movable. And so they did hundreds of different experiments. I've got some readings, literally like 20 or 30 different classes of experiments. But here's one interesting one, which was to transplant skin patch. And like I said, these are all based on human surgeries. So this was from a human surgery. So if you really mess up your hand and you mess up your thumb innervation, one of the things about the thumb is you often grab stuff with your thumb and other fingers, and so it really helps to have some sensation on your thumb. And so what the enterprising surgeon said was, let's get some skin from your little finger, leave its nerves attached and its blood supply attached. This is a microsurgery, and then manipulate it to go across your palm and paste it onto your thumb. So make a little cut here, make a little cut, and then actually put the nerves with the wires attached to it and actually paste that little skin patch on your thumb. So that's a surgery you can do. So what will happen after you've done that? Well, if you touch that skin patch, it'll feel like your little finger. Not surprisingly, because you came from the little finger. But it turns out just a couple weeks later, it starts feeling like the thumb again. And so somehow the maps have all sort of rearranged themselves so that the skin that used to, when you touched it, used to activate the little finger, now activates the thumb. And it just happens in just a couple weeks. And it's clearly driven by some kind of Hebbian process, because it will happen in 2 weeks in this case, but if you do something like bandage the hand up so that you can't touch stuff and sort of get the new correlation pattern, it won't work. It won't reorganize. Same way with the transplant skin patch. So if you just transplant the skin patch and don't touch it, it won't work. So it requires the actual sort of active experiencing the correlation pattern of the world coming in through your different fingers in order for this reorganization to take place. So transplant skin patch, that was little finger patch to thumb, and then 2 weeks later, patch feels like thumb. So, and then what about just practice? I always used to say, I just practice my guitar a lot, practice. What if you just just touch something a lot? If this whole system is sensitive, Merzenich did a lot of these experiments. So what about if you just touch something a lot? So owl monkeys have quite a long middle finger, and so they trained an owl monkey to just use its middle finger and just do a whole bunch of tasks just with its middle finger and no other fingers. And what happened in that case? Well, the middle finger got big. So after a month of practicing with its middle finger, what happened is it got this really big middle finger. And so here's 3. So 3 got really big, and it kind of intruded on. So here's 1, 2, 4, and 5. So 4 and 5 got smaller. And when I first heard this, is well, if I practice my guitar too much, is that going to invade part of visual cortex, or is it going to use up something else? And the answer is, it doesn't go very far. It just kind of cannibalizes some of the nearby fingers. It doesn't go into auditory cortex. It doesn't go into visual cortex. It just sort of temporarily expands this this middle finger representation. So so just practicing. And so then this, Merznick eventually had a company where they would try to practice makes perfect. Just practice a lot and you'll make your brain better. But where is this actually occurring? So everybody assumed when they looked at this that it must be occurring in the cortex. And the thing that really convinced people were these experiments where, just one-of-a-kind experiments where all the input, there's the central sulcus, all the input, so normally you start off with, face, then hand, and foot. So what if we got rid of all of the input to the hand, all the sensory input, pain, touch, everything? In this one-of-a-kind experiment done in the 80s, they discovered that the face completely invaded all the space up to the foot. So these things are just, a few millimeters. Here, you're just moving a few millimeters. Here, you're moving, this was a movement of, move, say, 2 centimeters. And 2 centimeters is enough that you probably had to have some kind of sprouting for this to occur. So this, if you want to look this up, this is the silver spring monkeys. So people assumed that must be in the cortex because the cortex is God, and the cortex should be the thing that is doing plasticity, learning, sort of things like that. Turns out it's not in the cortex. Not in the cortex. So how can this work? So if we let's look at the various stages. So here's the cortex. There's area 3B. And here's the ventral basal nucleus. And then here's the cuneate nucleus. That's the dorsal column nucleus. And then here's the actual skin down here. And here's a little receptor in the skin, Merkel disc. And then here's a ganglion cell. And it goes up, projects up into that ganglion cell projects up into the cuneate, and there's some spread. And then we've got another cell in the cuneate, and that goes up to the ventral basal nucleus, and it has some spread. And then there's ventral basal nucleus, goes up to area 3B, and that has some spread. Always, consider all the parts. So how do you remap something? So the way you remap something is, why don't we just turn up the synapses on the right side of these terminals? So here's some synapses on the right side of the terminals. We could do it anywhere. We could do it here. We could do it here. Everybody's assuming it was happening in the cortex. So what does that do? If I make the synapses that are on the right side of the terminal, of the axon terminal, stronger. So it's a little confusing. It's going to move the receptive field to the left. So so you have to just convince yourself that this is true. So strengthen synapses, existing synapses on right side of axon terminals. So if we do that, what is the implication of that? The implication is receptive field moves left. So this is on the right side, it moves left. And so why does that occur? Well, let's just take another one down here. Okay, so here's another ganglion cell that's nearby. That guy goes up like this, and it branches like this. And so you can see if we make the synapses of that guy stronger on the right side of that terminal, it's going to cause the receptive field to move this way. So that means that this left one is now, because it's got stronger right synapses, going to activate the same cortical cell here that we're recording from. So here's what we're recording up here. So that's a little confusing, but you can see you've got spread at every level, and so it seems sensible that you've got some existing synapses. If we just tweak the right side of everybody's axon terminal, well, then it's going to make our receptive field move left. So it moves left down there. So what did people do? They finally, after all this time, tried to see whether the reorganization was occurring in the cortex. And so what did they do? They did something like this. Where you get a major reorganization where the face has completely invaded the hand. So when you record from what used to be the hand, you've got face receptive fields in this location that used to be the hand. So this was, was hand. So this big reorganization has taken place. Was hand, now face. So what happens if you do that experiment? So let's just draw a picture here. Here's the boundary between the face and the hand. So here's the hand. You got all those things like that, and you got the hairy part over here, etc. This is 3B. So what happens if we do an injection of tracer into the face? It's connected up to other parts of the face, and it comes up to this border between the hand and the face and stops cold. So it's not the cortex, not even slightly. So you're recording from a cell here. It's got a representation of the face. It's not coming from the cortex. So this whole plasticity thing is not occurring in the cortex, amazingly. And so then enterprising researchers said, well, what if we go down to ventrobasal? Maybe it's occurring in ventrobasal. And they looked down at ventrobasal, no dice. The ventrobasal is going to the right part of cortex. The right part of the cuneate is going to ventrobasal. So it wasn't ventrobasal. So it's down in the spinal cord and the cuneate nucleus is where this is occurring. And it's a remarkable piece of research. It's completely, because it goes so much against the way people are thinking. Like back to my first lecture, sort of folk theories of the brain. You're assuming, well, we've got some plasticity. Well, what's plastic? Well, the cortex is plastic. The cortex is, all the good stuff happens in the cortex. So the cortex should be doing this reorganization. And because this finding is so strikingly against what everybody's assumption is, you probably haven't heard of it. And I always make the point with experiments like this, these are the most important experiments, because a lot of experiments you do, you're expecting the result. You're expecting it must have been the cortex. And so if this worked out that there was a big sprouting of axons in the cortex that was responsible for this reorganization, well, that would have been what people were expecting, and then people would have said it supports our existing finding, our existing sort of understanding. When you do this experiment, you see there's absolutely no expansion of connections in the cortex, where the cortex is going and attaching, doing something that could cause the hand representation to respond to the face, and it just says 0. It's just not happening. Not happening in the ventrobasal either. When you actually get that data back, that's the most important data, because it violated some kind of expectation of the way things are. And that's also the hardest data to get published, because people say, I don't believe it, it's got to be in the cortex. So it turns out probably all of this plasticity, this somatosensory plasticity, is basically occurring down in the cuneate and the spinal cord. So it's an important finding. So, your spinal cord's smart. Communicates smart. Okay. Okay, I think we'll end the recording there, Stan, and I'll take some questions.